Hello friends, welcome to my lecture on power series. A power series about a point x equal to a or centered at x equal to a is an expression of the form sigma n equal to 0 to infinity Cn x minus a to the power n, where a and Cn are real numbers. The Cn's are called the coefficients of the power series. Now, in the discussion of power series, the convergence of the series is a major issue. So, we will have to deal with this convergence question. A power series may converge for some values of x and diverge for some other values of x. We shall show that there is a number r, so that the power series converges for mod of x minus a less than r and diverges for mod of x minus a greater than r. The number r is called the radius of convergence of the series. The power series we shall see may or may not converge for mod of x minus a equal to r. That means, a minus r at x equal to a minus r and at x equal to a plus r. The convergence of the power series will have to be checked separately, and it may turn out that at these 2 points the power series may or may not converge. So, but this will not change the radius of convergence. The interval of all x's including the end points, if need be, for which the power series converges, is called the interval of convergence of the series. The interval of convergence therefore must contain the interval a minus r less than x less than a plus r, that is the open interval a minus r to a plus r. Since the power series converges for these values, thus to completely identify the interval of convergence, we have to determine if the power series converges for the endpoints x equal to a minus r or x equal to a plus r of the interval a minus r to a plus r. So, if the power series converges for one or both of these values, then we shall include them in the interval of convergence. Now, we can see one thing, that the power series always converges at its center, that is x equal to a, because if you put x equal to a in the series expression sigma n equal to 0 to infinity C n x minus a to the power n, you see that except the term C naught, all other terms vanish. So, sigma n equal to 0 to infinity C n x minus a to the power n at x equal to a gives C naught, okay, and therefore, the series always converges for x equal to a. Thus, even if the series may not converge for any other value of x, it is guaranteed that it always converges at its center, that is x equal to a. Now, how to determine the radius of convergence of the power series? We can apply the ratio test, or we can also apply the root test. If you want to apply the ratio test, then since the coefficients of the series are Cn's, we will have to find out the limit of mod of Cn plus 1 over Cn. If this limit is equal to L, where L is of course positive, because we are taking the limit of positive real numbers, okay. So, where L is greater than 0 or L is equal to 0 or L could even be infinity, and then the power series will have the radius of convergence r equal to 1 by L. So, if it is if it gives L equal to 0, then r will be infinity, and if L is equal to infinity, then r will be equal to 0, okay. So, in some cases we shall see that it is better to use, instead of this ratio test, we can use the root test, that is we can find the limit n tends to infinity mod of Cn raised to the power 1 by n. So, if this limit is equal to L, then the conclusion of this theorem will always also hold for this root test. So, if limit n tends to infinity mod of Cn to the power 1 by n is equal to L, where L is greater than 0 or L is equal to 0 or L is equal to infinity, then the power series sigma Cn x minus a to the power n, where n varies from 0 to infinity, will have a radius of convergence r equal to 1 by L. And so, where if L is 0, r is infinity, and if L is equal to infinity, then r is equal to 0. So, we can either apply the root test or apply the ratio test. This we will decide from the form of the power series. Okay, so for example, let us consider the series sigma n equal to 0 to infinity x minus 6 to the power n divided by n to the power n. So, this series is of the form sigma n equal to 0 to infinity C n x minus a to the power n. Here n C n is equal to 1 by n to the power n and a is equal to 6. So, we have a power series with center at x is equal to 6 and the coefficients of the series are given by 1 by n to the power n. Okay. Now, let us find so if you can see here when you have C n equal to 1 by n to the power n, it is better to apply the root test. Okay. So, limit n tends to infinity mod of C n to the power 1 by n, let us find this. So, this is limit n tends to infinity 1 by n to the power n raised to the power 1 by n. So, this will be equal to limit n tends to infinity 1 by n, which is equal to 0, and so L is equal to 0 here, which implies that R is equal to infinity. Okay. R is equal to infinity, and as we have seen that this power series always converges at its center. So, the power series given power series converges at x is equal to 6, and therefore, the series converges for all values of x from minus infinity to infinity. Okay. So, radius of convergence is infinity. What we find is the conclusion is that the given series converges for all values of x, that is minus infinity less than x less than infinity. Now, here you can also use to determine the value of L, you can also use the root instead of root test, the ratio test. If suppose you want to apply the ratio test, then you will have to find limit n tends to infinity mod of C n plus 1 over C n. Okay. So, this is limit n tends to infinity. Now, C n plus 1 will be 1 by n to the plus 1 raised to the power n plus 1. Okay. And then C n is 1 by n to the power n. So, n to the power n divided by n plus 1 to the power n to the power n, what I will get 1 over n plus 1 plus 1 by n to the power n into 1 over n plus 1, right. So, when we apply the ratio test, what we have to find limit n tends to infinity mod of C n plus 1 over C n, and what we get is 1 over n plus 1 to the power n plus 1 into n to the power n as n goes to infinity, and you can write it as n to the power n over 1 plus 1 by n plus 1 to the power n, which is 1 over 1 plus 1 by n to the power n into 1 by n plus 1. So, as n goes to infinity, 1 over 1 plus 1 by n to the power n tends to E, and 1 over n plus 1 goes to 0. So, this is equal to 0. Okay. So, L is equal to 0, and therefore, R is equal to infinity. The series converges at x equal to 6. So, the series converges for all real values of x. So, we can apply both the tests, the root test as well as ratio test here, and we can obtain the value of R and the interval of convergence. Okay. Now, let us consider another example, sigma n equal to 0 to infinity n factorial 5x plus 3 to the power n plus 1 whole square plus 4 to the power n. The given series first will have to be brought in the form of the standard power series. So, sigma n is equal to 0 to infinity, and we have to take n factorial 5 to the power n and then x plus 3 by 5 raised to the power n divided by n plus 1 factorial n plus 1 square plus 4n. Okay. So, here is C n is equal to n factorial 5 to the power n then over n plus 1 square. So, n plus 1 square means n square plus 2 n plus 1. So, n square plus 6 n plus 1. Okay. Now, hence limit of mod of C n plus 1 over C n. Okay, so n plus 1 factorial 5 to the power n plus 1 divided by n plus 1 whole square plus 6 times n plus 1 plus 1 into 1 by c n. So, n square plus 6 n plus 1 and then we have n factorial and 5 to the power n. Okay. So, this is how much? Now, let us see n plus 1 factorial over n factorial is n plus 1 n plus 1 5 to the power n plus 1 over 5 to the power n is 5 and we have then n square plus 6 n plus 1 divided by n plus 1 whole square means n square plus 2 n plus 1 plus 6 n plus 6 plus 1. So, means we have n square plus 8 n and then we have 1 plus 6 plus 6 1 plus 6 plus 1. So, we have 8. Okay, now, let us see this is a polynomial in n of degree 2 and the denominator is also a polynomial of polynomial in n of degree 2. So, n square plus 6 n plus 1 over n square plus 8 n plus 8 will tend to 1 as n goes to infinity and n plus 1 will go to infinity. So, the limit is infinity. Okay. And therefore, L is equal to infinity here, which implies that R is equal to 1 by L is R is equal to 0. So, R is equal to 0 and since we know that the series always converges at its center. So, the series converges for x equal to minus 3 by 5. So, the given series converges only for x equal to minus 3 by 4 minus 3 by 5. And nowhere else. Okay. Let us now consider the series sigma n equal to 0 to infinity 3x plus 4 to the power n over n cube plus 2 into 3 to the power n. So, here again we let us write in the standard form n is equal to 0 to infinity and 3 to the power n and then we have x plus 4 by 3 raised to the power n divided by n cube plus 2 into 3 to the power n. Okay. So, this gives C n is equal to 3 to the power n divided by n cube plus 2 into 3 to the power n. So, we get 1 by n cube plus 2. Now, let us find limit n tends to infinity mod of C n plus 1 over C n. So, this is limit n tends to infinity 1 over n plus 1 whole cube plus 2 and here we have n cube plus 2. Okay. So, numerator is a polynomial in n of degree 3, denominator is also a polynomial in n of degree 3. So, we see that the limit is equal to 1. Okay. So, here radius of convergence is r equal to 1 by L, this is L. So, L is equal to 1. So, R is equal to 1. So, radius of convergence is equal to 1 and therefore, the series converges mod of x minus 4 by 3 less than or equal to 1. Okay. Or I can say x minus 4 by 3 minus 1 is less than or equal to x minus 4 by 3 less than or equal to 1, which gives you 4 by 3 minus 1 less than or equal to x less than or equal to 4 by 3 plus 1. So, what we get is this is x plus 4 by 3 yeah, because the center is minus 4 by 3. So, this is plus 4 by 3. So, I get here minus 4 by 3, here also minus 4 by 3. So, this is minus 7 by 3 less than or equal to x less than or equal to minus 1 by 3. So, this is the interval of convergence. Okay. Now, for any x in the interval of convergence, the sum of the series defines a function of x, which let us denote by f x. F x is equal to sigma n equal to 0 to infinity C n x minus a to the power n. Now, the question arises whether the function some function f x is continuous or it is differentiable, whether the series can be differentiated term by term or integrated term by term. So, the answer to these questions lie in the uniform convergence of the series, whether the series converges uniformly and where. Okay. So, let us see, we have to answer this question. The theorem which answers this question is a power series converges uniformly to its limit in the interval of convergence. So, this means that if f x is the sum function of the series and the radius of convergence of the power series is r, then this and the center of the series is a, then the series always converges uniformly in the open interval a minus r less than x less than a plus r. Okay. So, let us see how we prove this. So, let us assume that the power series is given by and let r be its radius of convergence. Okay. Now, let us choose a number, let r be its, we are taking the power the convergence radius of convergence to be positive. Okay. Because if r is equal to 0, then the series converges only at the center. So, the question of uniform convergence does not arise. So, let us take r to be a positive number. So, let r be its positive radius of convergence, that is r is greater than 0. Okay. So, let us choose a number, say rho, such that 0 is less than rho less than r. Okay. So, then what we do is, let us take an x. Okay. So, let us say this is your interval 0 to r. Okay. This is your interval 0 to r. We take a positive number rho which lies in between 0 and r. Okay. So, rho is greater than 0, but less than r. Now, let us choose a point x, okay, such that okay, let us then okay, we can say for any x in the interval in the interval x minus we have mod of x minus a less than rho. Okay. Let us see what happens, let us see what happens to the power series. Okay. So, convergence of power series. So, mod of Cn mod of x minus a raised to the power n is then less than mod of Cn rho to the power n. Okay. Let us take the nth term of the power series, which is Cn x minus a to the power n. Then we notice that the nth term of the power series modulus of that mod of Cn mod of x minus a to the power n for any x in the interval mod of x minus a less than r satisfies this inequality. This is less than mod of Cn into rho to the power n. Let me take it as mn. Okay. Then the series sigma n equal to 0 to infinity mn is a convergent series. Let us see why it is a convergent series. We can apply ratio test. Okay. Mn is mod of Cn raised to the power 1 by n. So, sorry, we can apply the root test. So, by root test limit n tends to infinity mn to the power 1 by n is equal to limit n tends to infinity mod of Cn raised to the power 1 by n into rho to the power n whole to the power 1 by n. So, this is limit n tends to infinity mod of Cn raised to the power 1 by n into rho. Now, we know that the radius of convergence of the power series given power series r. So, limit n tends to infinity mod of Cn raised to the power 1 by n is equal to L. So, this is L into rho, but L is equal to 1 by r. So, this is rho by r. Okay. Rho by r means a positive, because we are taking r to be greater than 0. So, since r is greater than 0, okay, rho by r is a finite quantity. It is a finite quantity. It is a finite quantity, and therefore, the series sigma n equal to 0 to infinity m n converges by root test. So, this means that by Weierstrass M test, okay, by Weierstrass M test, the series sigma n is equal to 0 to infinity C n x minus a raised to the power n, okay, converges uniformly in the interval mod of x minus a less than rho. Okay. That means a minus rho less than x less than a plus rho. Now, since rho is arbitrary, okay, rho is any number which is greater than 0 but less than r, okay, we can go as close to r as possible. Okay, this implies that the given series converges uniformly in the interval a minus r to a plus r. Okay. So, a power series converges uniformly to its sum function in the interval of convergence, that is a minus r to a plus r, if a is the center of the series. Okay. Now, so we can conclude that the limit function f x. Now, we know from the theory of functions of a real variable that if a infinite series of functions of x converges uniformly over an interval I, then the sum function of the series is continuous. So, the limit function f x will be continuous in a minus r to a plus r. Now, let us suppose we can now state this corollary. Suppose f x is equal to sigma n equal to 0 to infinity C n x minus a to the power n converges uniformly in the range mod of x minus a less than r, then if mod of minus, if alpha beta is a closed interval which is lying in the range which is lying in mod of x minus a less than r, okay, see then if minus r is less than alpha less than beta less than r, we have integral alpha to beta f x dx equal to sigma n equal to 0 to infinity. So, we can integrate the function f x over the interval alpha beta. Okay. This we know again from the theory of functions of a real variable, that if we have an infinite series which converges uniformly over a closed interval I, then the sum function and the sum function is f x, then integral over I f x dx is equal to sigma n is equal to 0 to infinity integral over I of the nth term of the series. So, here integral over alpha beta f x dx will be sigma n equal to 0 to infinity C n integral over alpha to beta x minus a to the power n dx. So, the term series can be integrated term by term over any closed interval alpha beta contained in mod of x minus a less than r. So, that is what I had to do in this lecture. Thank you very much.